So in this next section, I want to talk about some of the reactions that we've seen before with epoxides, and then look at some new reactions. So we're going to talk about forming epoxides and how rings can open. Remember those epoxides, those are those three-membered ring ethers. So we've reviewed this reaction in one of our previous lectures with chapter 14, but let's do it again here. So let's take this and let's add McPba. Remember, that's a peroxy acid. And remember, the product that we get here is going to be an epoxide. So what's going to form is that three-membered ring, and it forms on both faces of our carbon-carbon double bond. So we're going to get this version where the oxygen's pointing backwards, but we're also going to get that same idea with the double bond pointing forward. So that's it. In that case, the relationship between these two things happens to be enantiomers. Now, the other way that we can do this is we can do something called base-promoted cichlization. So it's an SN2I, and the I stands for intramolecular, right? It means within the same molecule. So let me zoom in a little bit here, and let's take a look at this reaction. So let's start off here with that same molecule. And what we're going to do here is we're going to add H2O, and how about chlorine? So if you remember, what happens with this is that we form a halohydrin. So it's an OH and a halogen right on each one of those carbons. So a little bit of review here. Right, so one of the products is going to have our OH group pointing out here. Right, the methyl group would be going back. And remember that this occurs through a three-membered ring, right, that puts our chloro group here so that they're anti to each other. Right. And then the other thing that we get is the other molecule, the enantiomer of this. So that would be our OH pointing back and our chloro group pointing forward. And again, those are anti to each other. All right, so remember that mechanism. Review back chapter 8 if you need to take a look at that. Now, this reaction can continue here, and what we're going to do is just to make this a little easier so we don't have to draw these both out over and over again, let's just take this one. Let's imagine that we separated them out and that we're carrying out a second reaction in which we add something like sodium hydroxide. So NaOH is going to take this H away and make an ion there. So what we're going to get here is our oxygen, our methyl, and then our chloro group there. Right, so in essence here, hydroxides coming around, grabbing that H, and that bond right there is coming over here, right, and turning into acetylone pairs on the oxygen. All right, now here's where the SN2 part comes in, the SN2I part. So here we have our nucleophile. This guy's going to swing around and try to grab that carbon and kick off this as a leaving group. Now when that happens, we're going to form that same ring. And I want you to think about it this way, because remember, SN2 has inversion at the reacting carbon, right? So there's a couple ways to think about that. So here's the first way. H is pointing out at you right now. So when we get inversion, that H needs to pop back. So that H would be there. The other way of thinking about this is that that wedge, oxygen, that's going to stay on a wedge. There's no reason why it's going to move backwards or something. And we're going to end up having a wedge over here. Because to have trans next to each other like that's going to put a lot of strain on those bonds. So we get this. Right? And that's your product. And that, of course, is your CH3. Now, if we started with this, then we'd get that reacting also. So it would give us the enantiomer of this with our oxygen on the dash. Now, what we want to see is how we can open these rings up. That's our last couple reactions that we're going to see in this chapter. So we can do it under acidic conditions, and that we've seen before. So let's do a little review because it's something that's easy to forget, especially in this situation. So let's look at it again here. Let's just take that enantiomer from that reaction up above. And then, of course, we have lone pairs in here. So what happens in this reaction is that we add an acid. So H3O plus is something that we would write here often. Remember H3O plus. Looks like that. Now, in this situation, you have your oxygen, which has lone pairs on it, coming over and grabbing one of those H's. So here's what we're going to get. You have your oxygen here on wedges, one lone pair, and an H and a plus with a methyl group right there. Now, here's what we have. I want to point this out to you. It may not be obvious, but we have a three-membered ring. And then, so that's important, with a positive charge in the ring. So this is going to open up similar to all the reactions that we saw back in chapter 8. Right? So remember, you have a plus charge there. So what we do is we have these delta pluses. That carbon has a big delta plus because it has an extra R group on it. It's more substituted. And this is a smaller delta plus. Okay? So when that three-membered ring has a positive charge on it, the delta plus directs. Okay? That's also important. So, and again, this is not different than what we've seen really before. So, next up, right, we have H3O plus. So, water is part of that too. And so what happens is the water comes over and attacks that carbon, right? We lose this bond, and what we're going to end up with here is the following. And here's how we're going to reason through this. So there's no reason why that bond's going to change. So that's going to be my OH. Now we know that this is an SN2 type of a reaction here. And because of that, that's going to make our OH, 2 in this case, end up on the dash. So then that'll push the methyl up forward. And then the last step of this reaction is deprotonation. So we do that. And what we make here, it's kind of cool, but we make a diol. So you get an OH here, an OH here. All right, so there's your diol. They're trans to each other, and then don't forget our methyl group here. All right. Now the other thing that we can do here that's a new reaction is that we can do the same type of opening up with an acid like HCl. So the H3O plus there is from sulfuric acid or something like that. So let's look at that a little bit. So let's imagine here that you have ethylene oxide. Right, you add MCPBA. That gives us our epoxide here. Right? And then what we'd have here is HCl. So we would do this. Right, so that would form this. And then we have a ring opening essentially here. So chloride, right? This is like the cleavage of the ether that we saw in the previous reaction. It's just going to come over here and react at one of these sites. So then what you would have over here is a CH2 chloro group, right? So that's been added, and then an OH over here. Now that would continue. So we have another HCl there. So that's going to get protonated, and then we're going to substitute on that carbon down below. All right, so we're going to come over here and do that. That's going to give us that, and then I'll pull it down a little bit further. But chloride's going to come over here and react there, and then we have water leaving as your leaving group. So it gives you a Cl, CH2, CH2, Cl. You've made a dialkyl group, right? A vicinal dihalide, but you could do that synthetically by just taking the alkene and adding chlorine, right? Anyway, interesting little reaction that's still included in your text, but synthetically it's not very useful. Now, the last reaction that we're going to see here is ring opening under basic conditions. Now, let's take a look at it. So depending on what we use, an OH minus, you get diols. If you use an RO minus, then you get an alkoxy alcohol. But the mechanisms are going to be the same. So let's take a look at it down below, and we'll do kind of two flavors of it. Now, one thing that's important here, and this is something that pops up, so make sure you guys know this, is that regioselectivity under basic conditions is different than the regioselectivity under acidic conditions. So let's take one of those epoxides from before, with this guy, and let's take a look at what happens here when we add RO minus. Okay. Now synthetically we could make this by taking an ROH, and if you remember from the alcohols chapter, you could add like solid sodium or potassium. That would do that. But anyway, that's going to be our reactant here. Now, here's the deal. I want to point this out to you. We have a 3-membered ring. Okay, but we have no charge. All right? So because there's no charge, we don't really have that delta plus director anymore. So what directs us here is sterics. Okay, so then how does that work? Well, let's look at it. So here you have a CH3 group, right? You have this carbon over here. You've got an oxygen right there and another carbon. This side has less steric interactions or hindrance because this little h is small. So what happens is this comes around and attacks this bottom side, okay? And then we do this. Now what we're going to get there, let's see if we can draw this out. So get your ring in there. So that carbon that's dotted green is here, and it's still going to have a CH3 pointing back, and now that oxygen is going to be pointing forward with a minus charge. And it's SN2, so the H that's pointing back is going to swing forward. What's going to end up happening is it puts our OR group on the dash there. And then the last step of that reaction is that you take a hydrogen from the solvent. So when you have an alkoxide like this, it's usually also in that as a solvent too. All right, so we swing around and it's just a workup essentially here. So what that's going to give us is our CH3 and our OH. And then we're going to end up down here with your OR group. Okay? So this is an example of where we have an alkoxy and an alcohol. If we use hydroxide at this step rather than an alkoxide, then this would simply just be an OH. All right? Now, last reaction of the semester, guys. So congratulations. You've made it this far. You should be proud of yourself. It wasn't easy. We're going to start off with a different base. So same idea, but let's just do this just to make it a little bit different. Let's take this structure. So that's the enantiomer of the compound that we just drew up above. Now what I want to do is this, is I want to carry out this reaction, and I want to add, number one, a Grignard reagent. So let's just add, how about here, CH3 MgBr, and that has to take place using diethyl ether. So remember that these Grignards react like they're just free carb anions. So again, three-membered ring, no charge, sterics. Steric directs us to attack right there. So we do this. So this reaction is important to point out because we're making a new carbon-carbon bond. Now remember that dash is still going to be where the oxygen lives. Okay, and then pointing out here is going to be our CH3. We know that's the case because when three-membered rings open, we always open them anti. That doesn't really change. That's something we've carried throughout the semester. And then the last step here is that we're going to take this and we're going to do, so this is a separate step, we're going to add H3O+. So we're going to swing around and we're going to do this. And what that gives us is that same compound, except now we're protonated, right, on that oxygen, and you got your CH3 here. So I want to point out this bond right here. This is an important thing. Here we have a new carbon-carbon bond. So that becomes important when we talk about multi-step synthesis and stuff like that also, right?